this lesson, we're going to be solving this problem. This problem is under a shock loading. The problem statement, it reads as follows. A mass of 40 kg falls freely through a height of 2 meters onto a collar which is firmly attached to a lower end of a vertical steel bar. The bar is 2.5 millimeters in diameter and 6 meters long, and we are given the Young modulus 200 gigapascal. Then we're asked to calculate the stress here. We're asked to calculate the stress and we're asked to calculate the strain energy here. Whereas we're given the height, this is a height, we're given the mass, we're given the diameter, we're given this is a length. Let me draw a sketch to illustrate more about this problem statement. Here we've got the ceiling here. This is a ceiling, and on this ceiling the bar is attached. Then this is a collar, this one here, down here it's a collar. It's attached here on the ceiling, and they say they release what? A mass. Say this is a mass that they release here. They release from top here where the bar is attached here on the ceiling. Where the mass is here, down to the collar here, that is a height. That's height, this one, it is 2. And from where here on the ceiling where the bar is attached down to here on the collar here, that is the length. The length is 6 meters long. Then they say this, it is 40 kg mass, this one, that is the release freely to fall here on the collar of this. Then here, this channel, this bar, it's the same from top here till here on the bottom. This has got a diameter. That diameter is 2.5 millimeters. Then this 2.5 millimeters, it is 2.5 times 10 to exponent negative 3 meter. That is this. Then here, from the problem statement, we're asked to calculate the stress. Stress is equal to a force divided by the area. Let us find the area. The area is equal to pi. Then the diameter is 2.5 times 10 to exponent negative 3 squared divided by 4. Then this, it's gonna give the area to be 4.9 times 10 to exponent negative 4 meter squared. That is the area. That means we have the area now, but we don't have the force. So to find the force, we have to apply the shock loading formula. The shock loading formula, it is mg, open bracket, the height, this height, plus the change in length, of which it is force times the length, divided by area times Young modulus. Then close bracket equal to times the strain energy, of which it is force squared times the length divided by 2 times the area times Young modulus. That is the formula for shock loading. Here we will find the force that we are looking for. Let us see, we have the mass here, that 40 kg here. We have the gravity, we have the height, this height. We have the length, this length. We have the area, we have Young modulus. Also this side length, we have area Young modulus. What we don't have is this force that we're looking for in order to come and substitute in this formula to find the stress. So here, let us proceed. Let us substitute on this formula. The mass, it is 40 times the gravity, it is 9.81. Then open bracket, the height is 2 plus the force we don't have times the length is 6 divide the area is 4.9 times 10 to exponent negative 4. Then Young modulus is 200 times 10 to exponent 9 is equal to, then the force we don't have, times the length is 6, divide by 2 times, then with this unknown, let us move up a little bit. Then from here, on this side here, when you say this times this, gonna get 784.8. Then when you say this and this, say plus, you're gonna get 2.4 times 10 to exponent negative 5 f, then equal to this. It's gonna give you 3.06 times 10 to exponent negative 8 f squared. It is a quadratic equation. Let us rearrange it and equate it to 0. And this, when we take all this to here, that side, it's gonna change sign. It's gonna be negative 2.4 times 10 to exponent negative 5f. Then also when you take this to across the equal sign, it's gonna be negative, all equate to 0. Then this, you can solve it. If you can solve it, you apply a square root formula. Then you give this is a, this is b, this is c. Then because we're looking for force, say force is equal to negative b plus or minus square root sine, it is b squared, negative 4 ac, divide by 2a. Then substitute on this formula, it's gonna be negative, then b, you take b with this sign, close bracket, plus or minus, open the square root sign, then b still, it is negative 2.4 times 10 to exponent negative 5, close bracket, squared, minus 4a, this a, it is 3.06 times 10 to exponent negative 8. Then c, it is negative 784.8, close bracket, 2a. That's how you substitute this. Then when you solve this, all this, it come down here. It is, because this negative and this negative, it's gonna give you positive 4 times 10 to exponent negative 5, then plus or minus, this is 9.81 times 10 to exponent negative 3, then divide by 6 and 12 times 10 to exponent negative 8. We'll take positive sign because the negative sign gonna give you a negative force. Then we'll take positive sign here. Let us proceed down here, times 10 to exponent negative 8. Then this, when you solve it, it's gonna give 160.5 kilonewtons. Gonna give you this, of which it is 160.5 times 10 to exponent 3 newtons. Got the force now. Let us go back to the stress formula. Stress formula, it is equal to a force divided by area. The force, this one, 160.5 times 10 to exponent 3. Then the area that we've got, it is 4.9 times 10 to exponent negative 4. When you solve this, it's gonna give you 327.55 megapascal. It's gonna give you 327.55 megapascal. This, it can be 327.55 times 10 to exponent 6 Pascal. Then here we've got the stress that we're required to find from the problem statement on question 1. Now we're on question 2. They say we must find the strain energy. So the strain energy, it is this part here. When you check here, this part here, it is, that is the strain energy. Then it went down here, here it is. Then we'll take it from here, that part for the strain energy. Then let us write it. It is a strain energy. It is equal to 3.06 times 10 to exponent -8 force squared. That is it gonna be. Then you put that force you've got here. It is 160.5 times 10 to exponent 3. Don't forget to put squared here, because here there's a squared here on the force. Then when you calculate this, it's gonna give you a strain energy to be 788.26 joules. That is the strain energy that we are required to find from the problem statement on question 2. You may calculate as normal like this. The strain energy is equal to a force squared times the length divided by 2 times the area times Young modulus. Then this, let us take it down here and substitute. When you substitute, the force is 160.5 times 10 to exponent 3. Then this is squared times the length. The length is 6 divided by 2 times the area, which is 4.9 times 10 to exponent -4 times Young modulus, which is 200 times 10 to exponent 9. Still, when you calculate this, it's gonna give you the same answer, this one, 788.26 joules. It's gonna give you the same answer. So that means we've got what the question was looking for. The stress, it is 327.55 megapascal. Then here we've got the strain energy to be 788.26 joules. That's how you calculate the shock loading problem.